A teaspoon of it weighs 1 billion tons. Not a bucket, not a swimming pool, not a lake. A teaspoon. 1 teaspoon of the material inside a neutron star, the amount that would fit in a coffee spoon, weighs more than every human being who has ever lived, combined, multiplied by 1,000. And that is not even the most disturbing thing about them. A neutron stars are what happens when a star between 8 and 20 times the mass of our Sun exhausts its nuclear fuel and collapses, not slowly, not gently, in less than a second. The outer layers of the star fall inward at 1/4 of the speed of light, compress the core to a density that does not exist anywhere else in the observable universe, and then bounce outward in the most violent explosion in the cosmos since the Big Bang. A supernova. What is left behind after the explosion, the compressed core, is approximately 12 miles across. 12 miles, the distance you could drive in 15 minutes on a motorway, containing between 1 and 2 times the mass of our Sun, packed into something the size of a city. This is a neutron star. There are approximately 1 billion of them in the Milky Way alone. If this is the kind of content that stops you, the subscribe button is directly below this video right now. Hit it. The Cosmic Depth posts new space content every few days. To understand why a neutron star is so extreme, you need to understand what is holding it up. Ordinary matter, the matter of planets, people, mountains, oceans, is mostly empty space. An atom is almost entirely empty. The nucleus containing virtually all the mass sits at the center, and the electrons orbit at a distance that, scaled up, is like a fly in the middle of a football stadium. The stadium is the atom. The fly is the nucleus. Everything else is empty. When a star collapses, that empty space is eliminated. The electrons are forced into the protons. The electromagnetic repulsion that normally keeps atoms separated, the force that prevents your hand from passing through a table, is overwhelmed by gravity. Every electron and every proton in the collapsing stellar core is crushed together to form neutrons, billions upon billions of tons of matter compressed until there is no space left between particles. What remains is, essentially, a giant atomic nucleus, a sphere 12 miles across made entirely of neutrons, packed as tightly as the laws of physics permit. The density is 100 trillion times the density of water. If you compress the entire population of Earth, all 8 billion people, into the density of a neutron star, the result would be smaller than a grain of sand. And a neutron star is not merely dense, it is fast. Neutron stars spin. When the core of the dying star collapses, its rotation speeds up dramatically. The same physics that makes a spinning ice skater accelerate when they pull their arms in. The massive stellar core pulls in from thousands of kilometers across to 12 miles across, and the rotation rate increases proportionally. Some neutron stars spin at extraordinary rates. The fastest ever discovered, PSRJ 1748-2446 AD, rotates 716 times per second, 716 complete rotations per second. The equator of this neutron star is moving at approximately 24% of the speed of light. At that speed, the star is approaching the rotational limit, the speed at which centrifugal force would tear it apart. At 76% of the speed of light, a neutron star would disintegrate. PSRJ 1748-2446 AD is nearly 1/3 of the way there. These fast-spinning neutron stars are called pulsars because they emit beams of radio waves and X-rays from their magnetic poles. like a cosmic lighthouse, and as the star rotates, these beams sweep through space. If Earth happens to be in the path of the beam, we detect a pulse of radiation every time the beam sweeps past. Some pulsars are so precise in their timing that they rival atomic clocks. The Pulsar P SRB 1937 plus 21, the first millisecond pulsar ever discovered, keeps time to better than 1 part in 100 trillion, a cosmic clock made of collapsed stellar material spinning hundreds of times per second. The magnetic fields of neutron stars are where the physics becomes genuinely extreme. Earth has a magnetic field. It is useful. It deflects the solar wind and makes compasses work. Its strength of the surface is approximately 0.5 Gauss. A typical neutron star has a magnetic field of approximately 10 to the power of 12 Gauss, 1 trillion times stronger than Earth's magnetic field. At that field, strength atoms cannot exist in their normal form. The electrons are forced into extremely elongated shapes, stretched along the magnetic field lines into cylinders. Chemistry, as we know it, is impossible. Materials at the surface of a neutron star are not in any state that exists anywhere else in the universe. But even the magnetic field of a typical neutron star is not the most extreme case. Some neutron stars, called magnetars, have magnetic fields of up to 10 to the power of 15 Gauss, quadrillions of times stronger than Earth's field. At this field strength, the quantum vacuum itself is affected. The magnetic field is strong enough to polarize empty space, to change the properties of the vacuum through which light travels, a phenomenon called vacuum birefringence, predicted by quantum electrodynamics and confirmed in observations of the neutron star RxJ 1.856.5-37054, means that light behaves differently depending on its polarization when passing through the intense magnetic environment near a magnetar. A neutron star's magnetic field is strong enough to change the physics of empty space. And magnetars do something else that nothing else in the universe does. They starquake. The crust of a neutron star, a rigid crystalline layer of neutron-rich nuclei, approximately 1 mile thick, can crack. The intense magnetic field slowly distorts the crust, and when the stress exceeds what the material can bear, a fracture occurs. The crust shifts by a distance smaller than the width of an atomic nucleus. In 0.2 seconds, this microscopic shift releases more energy than our sun emits in 250,000 years. On December 27, 2004, a magnetar called SGR 1806-20 produced a giant flare. The burst of radiation that reached Earth after traveling 50,000 light years was intense enough to partially ionize the upper atmosphere. It briefly outshone the full moon in gamma rays. It disturbed the ionosphere measurably. It lasted 0.2 seconds from 50,000 light years away. Two neutron stars can find each other. Gravity is patient. In a binary star system, where both stars are massive enough to collapse into neutron stars, the two neutron stars will orbit each other, slowly losing energy to gravitational wave emission, as we covered in our gravity documentary on this channel, and spiral inward over millions of years. Eventually, they collide. The merger of two neutron stars is one of the most energetic events in the observable universe. In the fraction of a second of the collision, the objects release more energy than our sun will emit in its entire 10 billion year lifetime. The gravitational waves from these collisions were detected by LIGO in 2017, the first neutron-star merger ever observed in both gravitational waves and light simultaneously. 70 observatories around the world detected the event at the same moment. The gravitational wave signal arrived first, the ripple in spacetime traveling at the speed of light, then the gamma ray burst, then the optical emission, then the radio and X-ray afterglow. The event, GW170817, confirmed in a single observation that gravitational waves travel at the speed of light. It confirmed the origin of gamma ray bursts, and it confirmed something that physicists had predicted but never directly observed. Neutron star mergers produce gold. Every gold atom in the universe, in your jewelry, in your phone, in the gold standard that backed economies for centuries, was forged in a neutron star collision. The extreme conditions of the merger, temperatures of hundreds of billions of degrees, a flood of free neutrons, create rapid neutron capture reactions that build heavy elements that cannot be produced in ordinary stellar nucleosynthesis. Gold, platinum, uranium, lead, all created in a collision of neutron stars and scattered across the galaxy when the merger ejects material at a significant fraction of the speed of light. The gold in a wedding ring took two neutron stars millions of years to spiral together and a fraction of a second to create. Now, the personal question: what happens if a neutron star comes near Earth? The answer depends on how near. At interstellar distances, thousands of light years, the primary concern is magnetar flares. We detected the SGR 1806-2 burst from 50,000 light years, and it affected our atmosphere measurably. A magnetar flare from a source within a few thousand light years could be significantly more damaging, potentially stripping away significant portions of the ozone layer and exposing the surface to intense radiation. There is no known magnetar within dangerous range of Earth right now. The nearest known neutron star, RxJ 1856.5-3754, is approximately 400 light years away. At that distance, it poses no threat. Its radiation is undetectable without dedicated instruments. But if a neutron star were to pass through our solar system, an event that has a non-zero probability over geological timescales, given the density of stellar remnants in the Milky Way, the gravitational effects would be catastrophic long before any direct encounter. A neutron star passing at the distance of Neptune from the Sun would gravitationally disrupt every planetary orbit in the solar system. Earth would be ejected from the habitable zone, the oceans would freeze, life would end. The probability of this happening in the next billion years is vanishingly small, but not zero. And there is a more extreme scenario. If a neutron star were to somehow fall directly toward Earth, something that has no realistic mechanism in the current configuration of the galaxy, but that the physics permits, the tidal forces would become significant when it was still millions of kilometers away. The gravitational gradient, the difference in gravitational pull between the near side and the far side of the Earth, would begin to stretch the planet. Earthquakes of unprecedented magnitude, volcanic eruptions across every tectonic boundary simultaneously. At closer approach, the atmosphere would be stripped. The oceans would boil. At the moment of impact, there would be no impact in the conventional sense. Earth would not survive as a distinct object long enough to experience a collision. it would be tidally disrupted, torn apart into a stream of debris orbiting the neutron star in the seconds before what remained reached the surface. None of this is going to happen. But the fact that objects this extreme exist, that the universe produces stellar remnants 12 miles across and 2 solar masses, dense, spinning 700 times per second, with magnetic fields that change the physics of empty space, in numbers of approximately 1 billion in our galaxy alone, is itself one of the most remarkable facts in astrophysics. We live in a galaxy full of them, spinning silently, some of them older than the solar system, some of them cooling slowly toward temperatures at which neutron star physics transitions into something we do not yet fully understand. Some of them paired with companions they are slowly consuming, stealing mass from an orbiting star, adding it to their own, until they approach the maximum mass a neutron star can support before collapsing further into a black hole. The neutron star is not a permanent object. It is a phase, a stage in the life of stellar material between the violence of the supernova and whatever comes next. And what comes next? The black hole, which we covered in a previous documentary on this channel, is where the physics becomes even stranger still. But for now, a teaspoon, 1 billion tons, 1 billion of them in the Milky Way, and the gold on your finger was made in their collision. If that changed the way you think about the most extreme objects in the universe, the subscribe button is directly below this video right now. Hit it, and I will see you in the next one.